Okay, I decided to go ahead and put together this short video. Some of you are having problems with the concept of frequency, energy, and wavelength as it's associated with light. So let's try a couple of these problems. All right, these are from Module 7 in chemistry. All right, the first one is, what is the frequency of a light wave that has a wavelength of 484 nanometers? All right, so what's the frequency of light that has a wavelength of 484 nanometers? All right, we know the speed of light is a constant, 3.0 times 10 to the 8th meters per second. You should go ahead and have that constant stored in your calculator. All right, so what is the frequency? Well, since c is equal to the frequency times the wavelength, when I divide both sides by wavelength, those cancel, and I'll get frequency is the speed of light, which is stored in our calculator, divided by the wavelength, 484 nanometers. Well, nano means -9, so we enter in our calculator 484 times 10 to the -9. Now remember that this looks like 484 double E -9 when you put it in your calculator. So 3.08 times 10 to the 8th meters per second, meters per second divided by meters is going to leave me with 1 over seconds. And the value of that, when I put it in my calculator, I get out 6.2 times 10 to the 14th, 1 over second, but 1 over second, 6.2 times 10 to the 14th hertz. 6.2 times 10 to the 14th hertz. So go ahead and put that in your calculator. Alpha C divided by 484 times 10 to the -9, and you should get 6.198, but 3.0 times 10 to the 8th, that's only 2 sig figs. Even though 484 is 3, our constant C is only 2, so my answer can only have 2. So we get 6.2 times 10 to the 14th hertz. All right, so this is how you change, if you're given wavelength, how you get to frequency. If you're given wavelength, does that relate to the frequency? Well, let's try a different problem. This time, let's go from frequency to wavelength. This time, let's go from frequency to wavelength. Okay, again, we remember the speed of light, the constant 3.0 times 10 to the 8th, is equal to frequency times wavelength. This time they're asking us, what is the wavelength? So wavelength equals question mark of a light with a frequency of 5.7 times 10 to the 14th hertz. Well, this time I'm solving for wavelength, so I divide both sides by frequency. And I end up with wavelength equals the speed of light divided by the frequency. So our calculator, again, we have C stored, and the frequency is 5.7 times 10 to the 14th hertz. Now C is in meters per second, so that's meters per second divided by hertz, otherwise known as meters per second divided by 1 over second. How do you divide by a fraction? You multiply it by its reciprocal. So that's meters per second times seconds over 1 means my answer is going to be meters. So now that I know what my units are, let's put it in the calculator. Okay, so that's alpha C divided by 5.7 second EE 14. 14. And that turns out to be 5.3 times 10 to the -7. Again, two significant figures. 5.3 times 10 to the -7 meters, which we may or may not recognize as 530 nanometers. But 5.3 times 10 to the -7 is also a correct answer. 5.3 times 10 to the -7 meters. Let's see if I can fix that, make it look a little clearer here. Times 10 to the -7. 5.3 times 10 to the -7 meters. All right, so the previous problem, we changed wavelength to frequency. In this problem, we were given the frequency and we changed it to wavelength. So those are the two purposes of this equation. The speed of light is the frequency times the wavelength. All right. Well, what do we use this for? What do we care about frequency and wavelength? We're actually more interested in energy. We're actually more interested when we talk about atomic structure. We're talking about the energy of the light emitted. The energy of the light emitted. So let's look at this one. If we have a light wave that has a frequency of 6.2 times 10 to the 20th hertz, why not? Oops, wrong one. Hang on. All right, if I have a light wave that has an energy of, has a frequency of 6.2 times 10 to the 20th hertz, what is its energy? Well, that's a straightforward application of energy equals Planck's constant, which again, that's a constant. It's stored in our calculators. 6.63 times 10 to the negative 34 joules per hertz times the frequency. So that's straightforward. Energy equals H times 6.2 times 10 to the 20th hertz. So this is joules per hertz times hertz. So my answer is going to be joules. So when I take alpha H times 6.2 times 10 to the 20th, I'll get 4.1 times 10 to the negative 13th joules. 4.1 times 10 to the negative 13th joules. So this is, if I'm given the frequency of a light, how do I find its energy? If I'm given the frequency of the light, how do I find its energy? I just multiply by Planck's constant. Okay, well, let's go the other way. Say I know that in order to de-excite, an electron's been given too much energy and it wants to go back to ground state, okay, and it's going to release a light wave. It's going to release a light wave. The difference in energy between this level and this level is 4.8 times 10 to the negative 19th joules. All right, it's right here. 4.8 times 10 to the negative 19th joules. So when I de-excite, when I go from a higher energy level to a lower energy level, back to ground state, it's going to release this much energy. What's the wavelength of that energy? Well, let's think about this. If I know the energy, do I know how to find the frequency? Sure. I take the energy divided by Planck's constant, and that will give me the frequency. Well, if I know the frequency, do I know how to find the wavelength? Sure. I take the speed of light divided by the frequency, and that leaves me with the wavelength. So let's try this problem. Let's try this problem here. I don't know how that got there. All right. So I have a wave that this much energy. How do I know that's energy? It doesn't say if a wave has energy of, it just says 4.8 times 10 to the 19th joules. Joules is a measurement of energy, right? Joules is a measurement of energy right there. That tells me that this is energy. So I'm going to take 4.8 times 10 to the negative 19th divided by Planck's constant, which is stored in my calculator, and that will give me the frequency. So I'm going to take 4.8 times 10 to the negative 19th divided by alpha H, and I'll get 7.2 times 10 to the 14th. 7.2 times 10 to the 14th. Now we can know frequencies measured in hertz, or we can check it. All right, so this is, joules divided by joules per hertz, right? Planck's constant is joules per hertz. How do you divide by a fraction? You multiply by its reciprocal. Joules cancel, leaves me with hertz. So this tells me that this amount of energy has this frequency, but it didn't ask me for frequency. It asked me for wavelength. So let's see if we can figure out what the wavelength is. All right, right here, the speed of light is a constant, and that's equal to the frequency times the wavelength. So the wavelength, let me bring it up here a little bit. The wavelength is going to be the speed of light divided by the frequency. So that's just going to be C, 3.0 times 10 to the 8th meters per second, divided by 7.2 times 10 to the 14th hertz. So kind of running into myself here, but if I'm going to use these units up here. If I have meters per second divided by hertz, well, a hertz is 1 over second, so that's meters per second divided by 1 over second, flipping times seconds over 1, and that's going to equal meters. So my wavelength is going to be measured in meters. Let's see what the value is. I'm going to take alpha C divided by 7.2 times 10 to the 14th hertz, and that gives me 4.2 times 10 to the negative 7 times 10 to the negative 7 meters. 4.2 times 10 to the negative 7 meters. Now let's not forget what that means. That means if the difference in energy between this energy level and this energy level is 4.8 times 10 to the negative 19 joules, whenever an electron de-excites, it will emit a wave with exactly that wavelength. This amount of energy is associated with this wavelength, 4.2 times 10 to the negative 7 meters. Well, let's go the other direction. Let's suppose I'm observing some a particular material, and it's de-exciting, and as it's jumping down, I'm able to measure that it's releasing a wave that has a wavelength of 412 nanometers. How much energy is it releasing? How much energy is being let go? How much energy is being released as it moves down an orbital, as it moves down 1 or 2 orbitals? How much energy is released with a 412 nanometer light wave? Well, this time, in order to find energy, I first have to find frequency. Well, I'm given wavelength, and I know how to change wavelength to frequency, so let's do that. To find the frequency, I'm going to take the speed of light and divide it by the wavelength. That's going to equal the frequency. See right here? Divide it by the wavelength. So the speed of light divided by 412. Now what did nano mean? It means times 10 to the negative 9. So take your calculator and do alpha C divided by 412 times 10 to the negative 9, and you'll get 7.3 times 10 to the 14th. Now remember, that C is only 2 significant figures. That's why I'm rounding this to 7.3 times 10 to the 14th hertz. 10 to the 14th hertz. Now I'm not looking for frequency, right? I'm looking for energy. So I'm going to have to go up here. Choose pink. I'm going to have to go up here and find energy. Well, energy is Planck's constant, h, times the frequency. Well, Planck's constant's in my calculator, and I just calculated the frequency to be 7.3 times 10 to the 14th. Planck's constant is joules per hertz. Frequency is measured in hertz. Those cancel. My answer is going to be in joules. So Planck's constant, alpha h, times 7.3 times 10 to the 14th hertz gives me an energy of 4.8 times 10 to the negative 19th joules. 4.8 times 10 to the negative 19th joules. All right, these are the problems that give students issues in Module 7. They're not hard. They're all just using these 2 equations and these 2 constants interchangeably, going back and forth, making a purpose out of all that algebra you've learned.